Autonomous coding agents rapidly transitioned from a novelty to systems building entire applications. Collapsing chaos into a single continuous loop provided unmatched reliability. This began with manual copy-pasting from ChatGPT, followed by IDE forks that integrated command line assistance directly into the editor interface. Today, the state-of-the-art has moved to headless CLI agents. These systems operate entirely in the terminal, managing end-to-end execution without manual code intervention. While underlying models have improved, much of this progress stems from radical architectural simplification. Developers are stripping away the complex logic once used to mask model limitations. We are mapping the internal mechanics of these modern headless agents to see how a minimalist design handles complex software engineering. Mastering this minimalist architecture allows developers to build new systems that scale without the weight of rigid legacy constraints. The first instinct when building an agent is to control every possible outcome to prevent the model from deviating. This usually results in directed acyclic graphs, or DAGs. These structures rely on branching paths and strict intent classifiers to force the model through a predefined workflow. Rigid DAGs often fail in general-purpose programming. Software development is too unpredictable. A fixed path cannot account for a missing dependency or a sudden environment error. Frontier agents utilize a simpler structure, the N0 master loop. The logic follows a repeating cycle. The system checks for tool calls, executes the requested tool, feeds the output back to the model, and continues until the task is complete. This design philosophy focuses on providing the model with tools and allowing it to manage the execution path independently. This relies on the base model's ability to self-correct. When an execution fails, the loop simply returns the error to the model, which then explores a different solution. Allowing a model to autonomously explore and correct its mistakes provides better handling of unpredictable edge cases than hard-coded routing. The master loop functions through a core suite of 4 tools: read, grep, and glob, edit, and bash. These agents frequently bypass complex vector databases in favor of native search tools like grep and glob, which interact directly with the local file system. Native file search mimics how human developers actually work. When you need to find a function, you search the code directly rather than indexing the entire project. The edit tool avoids rewriting entire files. Instead, it employs unified biffing, identifying and replacing only the specific lines that require modification. Unified diffs use fewer tokens and reduce the chance of the model inadvertently changing unrelated code during the rewrite. Bash serves as a primary interface between the model and the operating system. Large language models are well suited for shell interactions because their training data includes vast amounts of bash scripting and terminal command logs. Running in a sandboxed execution environment allows the model to test its own code and observe the results before finalizing a change. Combining native search, precise edits, and shell access transforms the agent from a simple text generator into a system capable of manipulating a local environment. The master loop faces a constant constraint: context window exhaustion. As the history of the conversation grows, the model's reasoning can begin to degrade. Every file read and terminal log adds to the context, pushing the model towards its memory limit. When reached, systems use context compression. It summarizes the middle portion of the log while keeping the earliest and most recent data intact. To manage this proactively, agents use sub-agents to handle data-heavy tasks. If the main loop needs to research a massive file, it prompts a sub-agent to perform that task in a separate context. The sub-agent processes the data independently and returns only a concise JSON result, keeping the primary loop's context clean. This isolation allows the system to analyze large code bases without overwhelming its primary reasoning capabilities with irrelevant data. Sub-agent design focuses on protecting the master loop by creating strictly isolated memory buffers for specific research tasks. In a flat loop architecture, the agent must have a way to stay focused on a long-term objective without losing track of its progress. State management is handled through the use of prompt-injected structured data. Frontier agents utilize a to-do list schema that tracks IDs, task titles, completion status, and hashes that point to specific evidence found during the run. The model dynamically generates and updates these to-do items as it completes various stages of the project. This generated JSON is injected directly into the system prompt, ensuring the agent's current objectives remain at the top of its context window. This discipline is maintained entirely through the model's instruction-following ability, rather than being hard-coded into the application's core logic. Prompt-based state management provides the structure necessary for complex tasks, while preserving the agile flexibility of the master loop. This architecture combines a central master loop, a targeted tooling suite, isolated tasks for research, and prompt-injected state management. Operating these systems requires a shift in how we evaluate code. Non-deterministic execution creates a unique challenge for standard testing. Traditional integration tests often struggle to account for the variety of paths an agent might take to reach a correct solution. Instead of testing the agent's specific path, developers must rigorously unit test the individual tools to ensure they provide predictable inputs and outputs for the model. Performance evaluation for the loop itself relies on measuring agent smell, tracking metrics like retry frequency, the rate of looping errors, and overall tool efficiency during backtesting. Building for an autonomous future requires deleting unnecessary scaffolding, protecting the context window, and trusting the model to orchestrate its own tools.